In February 1943, Air Marshal Arthur Harris read the proposal a second time, not because he found it compelling, because he needed to be certain he was reading it correctly. A civilian engineer from Vickers Aviation, a man who had never flown a combat mission, never commanded a squadron, never sat inside a briefing room with operational authority over anything, was proposing that the Royal Air Force destroy the Möhne and Eder dams by skipping a rotating cylinder across the surface of a reservoir, like a schoolboy skipping stones across a pond. Harris set the paper down. He had been running Bomber Command through the worst years of the air war. He had watched Lancaster crews die over Hamburg, over Berlin, over Cologne. He understood the cost of a mission better than any civilian engineer with a desk at Weybridge. And this man, this Barnes Wallis, was asking him to send aircraft at 60 feet above water in the dark, in the face of German flak, to deliver a weapon that had never been dropped operationally, against a target that the entire strategic bombing community had already determined was not worth attacking. Harris called it tripe of the wildest description. The Deputy Chief of the Air Staff, Air Marshal Norman Bottomley, reviewed the technical drawings and noted that the hydrodynamics appeared to be largely theoretical. The chief scientist at the Ministry of Aircraft Production, Ben Lockspizer, circulated a memo concluding that the operational concept was, in the precise language of British bureaucratic dismissal, not a practicable proposition. And they were not wrong. Based on every piece of evidence available to them in February 1943, they were making a completely rational professional judgment. That judgment would be reversed on the night of May 16th to 17th, 1943, between the hours of 0028 and 0056 over the Möhne Reservoir in the Ruhr Valley. But to understand what happened that night and why it still matters, you first need to understand what these men actually saw when they looked at Barnes Wallis's proposal. Because they were not stupid, they were looking at something that, on the surface, genuinely appeared to be impossible. Barnes Wallis had been working on the problem of dam destruction since 1940, not because anyone asked him to. Because he had done the mathematics on his own initiative and concluded that destroying Germany's water and hydroelectric infrastructure in the Ruhr Valley would be the single most efficient use of strategic bombing resources available to the Allies. The Ruhr was the industrial heart of Nazi Germany. The Krupp steelworks, the coal mines, the armaments factories, all of it depended on a network of reservoirs and dams that provided water for industrial processes, electricity for machinery, and regulated river flow for barge transport. The Möhne Dam alone held 134 million cubic meters of water. The Eder held 202 million. If both were breached simultaneously before the spring flood season, Wallis calculated, the resulting water shortage and flood damage would set back German steel production by a figure he estimated at somewhere between 3 and 6 months. The problem was the physics of the attack itself. A conventional bomb dropped from altitude onto a masonry gravity dam like the Möhne would not work. Wallis understood this immediately. The dam face was 34 meters thick at its base and 650 meters long. A bomb hitting the top or the upstream face would crater the masonry but not breach it. To create a structural failure, you needed to detonate a charge at the dam's base, at the point where the water pressure was highest and the structure was most vulnerable. But getting a bomb to the base of the dam face was geometrically impossible with conventional delivery. The attack corridor required the aircraft to approach at low level over the reservoir, which meant the bomb would enter the water at an angle and sink to the bottom at a point well away from the dam face. The water depth at the Möhne's base was between 9 and 12 meters. A conventional depth charge detonated at that depth, at that distance from the structure, would produce a pressure wave that dissipated well before it reached the masonry in sufficient concentration to cause failure. This is the problem Wallis had been solving since 1940, and the solution he arrived at looked, to every conventionally trained military mind who reviewed it, like something between a novelty and a hallucination. The cylinder had to skip. Here is the engineering logic that the Royal Air Force's senior officers could not initially see past the absurdity to appreciate. If the weapon was given sufficient backspin, Wallis calculated 500 rotations per minute, and dropped at precisely the right height and speed, it would behave on water the way a spinning projectile behaves on any semi-elastic surface. The gyroscopic effect of the backspin stabilizes the cylinder's axis on each impact, preventing it from cartwheeling. Each contact with the water surface transfers energy back upward rather than absorbing it, producing a controlled series of bounces that carry the weapon forward across the reservoir.
But the backspin served a second function that was even more important. When the cylinder reached the dam face and slid down into contact with the masonry, the backspin would continue to press it against the wall rather than allowing it to deflect away.
The weapon would then sink, pressed against the dam face by its own rotation to the optimal detonation depth of 9 meters. At that point, a hydrostatic pistol, an acoustic proximity fuse calibrated to water pressure at exactly that depth, would trigger the 2,994 kilogram Torpex charge. Torpex was 50% more powerful than TNT by mass. At 9 meters of depth, against a masonry face that transmitted pressure directly into a structure already under 1.34 million tons of water load, the detonation would not need to shatter the dam. It needed only to create a crack sufficient for the water pressure itself to complete the breach. Wallis had not invented a bomb. He had invented a system in which the weapon and the target's own stored energy were both components of the destruction mechanism. The RAF officers who called this absurd were evaluating the delivery method. Wallis had designed the delivery method as inseparable from the effect. They were reading a specification for a skipping stone. He had written a specification for a water pressure amplifier that happened to skip across a reservoir to reach its operating position. The distinction was everything. But knowing the logic was correct and proving it were two entirely different problems, and the proof, when it came, was not built in a laboratory. It was built on a flooded quarry in Hertfordshire, a reservoir in Kent, and eventually the Reculver bombing range on the Kent coast, through a sequence of trial drops that killed the first 3 prototypes and nearly killed the 4th. The early test models were wooden spheres. Wallis originally envisioned a spherical weapon, which offered better skip geometry on a theoretical basis. The first drops from a Wellington bomber over Chesil Beach in December 1942 produced mixed results. The spheres bounced, but the casing fractured on impact, destroying the spin stabilization mechanism. Wallis went back to the drawing board. Not to the concept was working, but to the geometry. The cylinder was the solution. Longer axis, greater rotational inertia, less surface stress per bounce impact. By February 1943, the redesigned weapon, now designated Upkeep, was clearing 400 meters per skip sequence in controlled trials. The problem remaining was the aircraft. A Lancaster modified to carry Upkeep externally, the weapon was too large for the bomb bay, so it hung from specially designed caliper arms below the fuselage, had to release at precisely 60 feet above water, at precisely 220 miles per hour, at precisely 425 meters from the dam face. Any deviation from these parameters would alter the skip trajectory and the terminal descent angle against the dam wall. 60 feet, in the dark, over a defended reservoir, in a 4-engine bomber. This is where Air Marshal Harris's skepticism was most operationally grounded. He was not wrong about the difficulty. He was wrong about the impossibility. Wing Commander Guy Gibson, the officer selected to command the new No. 617 Squadron, formed specifically for this mission, solved the altitude problem through a device of such primitive elegance that it became almost more famous than the weapon itself.
2 spotlights, one mounted under the Lancaster's nose, one under the fuselage, were angled to converge at exactly 60 feet below the aircraft. As the aircraft descended, the 2 spots of light on the water surface would approach each other.
When they merged into a single ellipse, the aircraft was at exactly 60 feet. The crews called it the figure 8 method. It worked on a principle a school physics teacher could explain in 5 minutes. The distance problem was solved by a triangular wooden sight, a simple piece of wood with 2 nails protruding from it, held up to the eye. When the 2 towers of the Moan Dam aligned with the nails on either side of the central sighting notch, the aircraft was at 425 meters. The crews could build one themselves with materials from a school workshop. No. 617 Squadron flew 173 practice sorties over British reservoirs between March and May 1943. They practiced the 60-foot runs at night until the spotlights and the triangle sight became second nature. They flew the approach corridors until they could execute them under blackout conditions with defensive fire simulation. By the time Operation Chastise was authorized, the 133 aircrew assigned to the mission had rehearsed it to a degree of precision that had never been achieved in any Bomber Command operation.
Harris, who had resisted the operation until February and authorized it only after direct air ministry pressure, had still not fully changed his mind about Wallis's weapon.
He wrote to the Chief of the Air Staff in April 1943, after the final operational approval, noting that the resources committed to this operation, 19 specially modified Lancasters and their elite crews, represented an opportunity cost from his main offensive that he found difficult to justify based on available evidence.
He would not have to wait long for the evidence. The night of May 16, 1943, was clear over the Ruhr, moonlit. The 19 Lancasters of No. 617 Squadron departed RAF Scampton in 3 waves between 21:28 and 0009 hours. The first wave of 9 aircraft, led by Gibson, flew the northern route across the Dutch coast at 100 feet, low enough to pass under German radar coverage, and turned southeast toward the Möhne. The German defenses at the Möhne reservoir were not trivial. Flak towers on both dam towers, light anti-aircraft guns positioned along the shore, and a network of searchlights whose operators had standing orders to watch for exactly the kind of low-level attack that was approaching. The Ruhr dams were on the German Air Defense Command's list of strategic targets requiring active protection.
The Wehrmacht had been warned about the possibility of attack. They had gun crews on the towers. Gibson made the first attack run at 0028 hours. Upkeep was released at 425 meters, at 60 feet, at 220 miles per hour, spinning at 500 RPM. The weapon bounced 3 times across the reservoir surface, struck the dam wall, slid downward against the masonry, and detonated at depth. The dam did not breach. Gibson assessed the strike from the air. A column of water had erupted 300 feet above the dam crest. The masonry appeared intact. He called in the second aircraft, piloted by Flight Lieutenant John Hopgood. Hopgood's Lancaster was already damaged. It had taken flak fire on the approach, and the bomb release was slightly mistimed. The weapon skipped over the dam parapet and detonated on the powerhouse below. Hopgood's aircraft, on fire and losing altitude, cleared the dam by less than 50 feet before crashing 3 kilometers beyond. Hopgood and 3 of his crew died. 3 parachuted to captivity. The third aircraft dropped successfully. Another column of water. Still no breach visible. The fourth, flown by Flight Lieutenant Henry Maudsley, suffered a weapon release malfunction. The bomb detonated on the dam parapet, damaging Maudsley's aircraft. He would not return from the raid. The fifth aircraft, flown by Flight Lieutenant David Maltby, dropped at 0049 hours. The Upkeep bounced 4 times, struck the dam wall center section, and sank. At 056 hours, the Möhne Dam breached. The wall failed not at the detonation point, but 77 meters to its left, where the cumulative pressure effects of 3 successful detonations had already stressed the masonry beyond its structural tolerance. The breach widened in seconds as the water load completed what the explosives had begun. Within 11 minutes, the gap was 77 meters wide and 22 meters deep. The entire contents of the Möhne reservoir, 134 million cubic meters of water, began moving down the Möhne Valley at a wavefront height of 10 meters, traveling at 6 meters per second. Gibson, circling above, transmitted the code word nigger, the signal that the Möhne had been breached, and led the remaining aircraft toward the Eder. The Eder fell at 0152 hours. 3 Upkeep bombs. The same mechanics, the same physics, the same result that every senior officer reviewing Wallis's proposal had concluded was impossible. Let me show you what happened in the Ruhr Valley in the hours after those 2 walls failed. The Möhne flood wave traveled 80 kilometers down the Ruhr Valley before its height dropped below 1 meter. In those 80 kilometers, it destroyed or damaged 125 factories, 25 road bridges, 21 railway bridges, 11 mine shafts, and 6,316 homes. The town of Nijheim-Hoesten,
9 kilometers downstream, was struck by a wall of water 6 meters high at 01:15 hours. The rail junction at Hamm, critical to Ruhr industrial logistics, was inundated for 96 hours.
The Eder flood wave extended 50 kilometers into the Weser Valley. 1,300 acres of agricultural land were destroyed. The hydroelectric output of both dam systems, critical to Ruhr steel and coal operations, ceased entirely.
The water shortage that followed persisted for 9 weeks. German industrial engineers, working directly with Armaments Minister Albert Speer's emergency planning staff, calculated that Ruhr steel production between June and August 1943 would have been 400,000 tons higher without the water supply interruption.
Speer himself, in his post-war interrogation by Allied intelligence officers on July 18, 1945, stated that the dam's raid had been the operation he feared most during the war, because the Ruhr's vulnerability to exactly this kind of attack had been the one variable that German industrial planning had never adequately resolved. The man who had called Wallis's proposal tripe of the wildest description was now reading Speer's interrogation report. Let me show you what that comparison between upkeep and conventional alternatives actually looked like when evaluated against a shared operational standard.
Conventional penetrating bombs of 1943, the 4,000-pound blast bomb, the 8,000-pound bomb, even the 12,000-pound Tallboy being developed concurrently by Wallis himself, all shared the same terminal geometry problem. A bomb released over a reservoir from an altitude safe enough for the crew would enter the water at an angle and sink on a ballistic arc that placed it 40 to 80 meters from the dam face at depth. At that distance, even a Torpex charge of 2,994 kilograms would produce a pressure wave at the dam wall of less than 300 pounds per square inch, insufficient to crack masonry 34 meters thick under static conditions, let alone under the stabilizing pressure of 134 million cubic meters of water. Upkeep detonated at 9 meters of depth, pressed against the dam face. The contact transmission of the pressure wave through masonry already under maximum compressive load from waterhead amplified the effective destructive force by a factor Wallis's calculations placed between 4 and 6 times compared to a standoff detonation at the same depth. The weapon was operating at 4,800 to 7,200 effective pounds per square inch of transmitted pressure. The Mohn's design tolerance under static load was 3,200. The math was not close. The RAF's conventional bombing option for dam destruction required aircraft at 10,000 to 15,000 feet, dropping bombs that would miss the target's vulnerable zone by geometry, regardless of accuracy. It was not a precision failure. It was a physics failure baked into the approach doctrine itself. The target's geometry made conventional attack not difficult, but structurally impossible to execute effectively.
Upkeep did not skip across the water because Barnes-Wallis was eccentric. It skipped because the only position from which a charge of that magnitude could transmit lethal pressure to the Mohn's masonry was 9 meters of depth, pressed against the wall's upstream face.
The skip was not the weapon's strange feature. The skip was the solution to a geometry problem that every alternative approach failed to solve. The Royal Air Force officers who dismissed the proposal were evaluating the delivery system in isolation. Wallis had designed the delivery system as the only possible path to the single position where the physics worked. You could not separate the skip from the effect. They were the same thing. Now consider what 617 Squadron accomplished with 19 aircraft. The Mohn and Eder dams were construction projects completed in 1913 and 1914 at a combined cost of 26.5 million Reichsmarks, equivalent to several hundred million pounds at 1943 values. They had been built to last a century. They had been designed with structural specifications sufficient to withstand conventional military explosive attack. German engineering on the Mohn Dam specifically had incorporated reinforcement measures that the designers believed made it immune to any foreseeable weapon delivery system. Both structures were destroyed in a single night at a total expenditure of 11 upkeep weapons. 8 dropped against the Mohn, 3 against the Eder. The cost to manufacture each upkeep cylinder was approximately 500 pounds. The total ordnance expenditure of the raid was roughly 5,500 pounds of manufacturing cost. producing damage that German industrial planners assessed at over 400 million Reichsmarks in direct economic impact. Against those 11 successful weapons, 617 Squadron lost 8 of its 19 aircraft and 53 of its 133 aircrew.
This ratio, 8 aircraft lost for 2 major strategic objectives destroyed, was exceptional by Bomber Command's operational standards in 1943, when area bombing campaigns over German cities sustained loss rates of 4 to 6% per mission, with significantly lower strategic returns.
Operation Chastise's loss rate was 42% of aircraft dispatched, but it was against a target that no other available method could have touched, against dams that German planners had assessed as untouchable. Barnes-Wallis himself calculated, before the mission, that the required minimum force to breach both primary targets was between 6 and 10 weapons delivered within specification. The actual result, 8 weapons within specification against 2 targets, both breached, fell within the upper range of his prediction, a deviation from the central estimate of less than 12%. He was not a man who had gotten lucky. He was a man who had calculated the physics correctly and waited 2 years for the institution to catch up. Albert Speer's testimony is the piece of evidence that closes this case most completely, not because Speer was inclined to generosity toward his enemies, because he was not. Speer was, by training and professional identity, an architect and industrial organizer. He understood structural engineering. He understood production bottlenecks. He had spent 1943 managing the emergency response to the Chastise flood damage, directing repair crews, reallocating water resources, negotiating emergency power supply agreements with unaffected industrial regions, and coordinating the rebuilding of the Möhne and Eder dams in a repair program that required 7,000 workers and did not restore full reservoir capacity until autumn 1943. He had personally supervised the emergency assessment of Ruhr industrial output against the water shortage projections. When Allied interrogators asked him in July 1945 which Allied bombing operations had most severely threatened the German war economy, Speer listed them in order. The dams raid was second, behind only the Ploiesti oil refineries. He specified that the Ruhr had 3 structurally critical vulnerabilities: water, electrical power, and transportation, and that the night of May 16th had simultaneously attacked all 3. He said that a follow-up operation against the remaining Ruhr dams in the summer of 1943 would have produced, in his direct words, catastrophic consequences for German armaments production. The follow-up raid never came. 617 Squadron's losses had reduced the available pool of trained crews, and Bomber Command's strategic focus had shifted to the oil campaign. The dams were repaired, but Speer's assessment stands as the testimony of the most qualified hostile witness available, the minister responsible for German industrial production, confirming, under questioning with no incentive to embellish, that a weapon every senior RAF officer had called absurd had struck at exactly the vulnerability he had feared most. The RAF called Barnes-Wallis's idea absurd because they were evaluating a delivery mechanism without understanding that the delivery mechanism was inseparable from the only position in the physical universe where the effect was achievable. They saw a man proposing to skip stones across a reservoir. They missed that the stones had to skip because the dam's geometry made every other approach physically incapable of working. This is the pattern that repeats across the history of military innovation. The institution evaluates the unfamiliar delivery method and misses the target physics. The inventor has solved the target physics and built the delivery method as its necessary consequence. The gap between these two perspectives, one focused on the method's strangeness and one focused on the problem's geometry, is the gap between dismissal and vindication. Wallis went through 27 months of institutional resistance. He funded early test models partially from his own salary. He produced 4 successive weapon variants before the geometry was right. He wrote 11 formal memorandas to Air Ministry officials, who returned them with skeptical annotations. He secured a meeting with Air Marshal Portal only by having a mutual acquaintance arrange it informally. He showed Portal 16mm film footage of Upkeep bouncing across the reservoir at Rekover. Portal approved the operation. The lesson here is not simply that a stubborn inventor outlasted a bureaucracy. The lesson is about the nature of the problem being solved. Wallis was not trying to build a better bomb.
He was trying to find the only position in space, 9 meters deep, pressed against masonry, where the physics of pressure transmission made dam breach achievable.
Once you understand that he was working backward from the physics of the target to the geometry of the delivery, the skipping stops looking like eccentricity and starts looking like the only logical conclusion available. Every great engineering solution looks obvious in retrospect. The reason it does not look obvious at the time is that most people evaluate new solutions against familiar methods rather than against the underlying problem. The Royal Air Force evaluated upkeep against conventional bombing doctrine.
Wallis had evaluated it against the structural mechanics of a masonry gravity dam under hydrostatic load. They were answering different questions. Only one of those questions connected to whether the dams would still be standing in May 1944. They would not be. Here's the question I want to leave you with. Operation Chastise is considered one of the most technically precise military operations in history. But the follow-up strikes, Spears said, would have been catastrophic. Never happened, because the institutional appetite for this kind of precision, low-level, single-target operation was never rebuilt after the losses of May 1943. Harris returned to area bombing. 617 Squadron eventually became a precision specialty unit, but it was never again used in the Ruhr Dam configuration. Was that the right strategic decision, or did the Royal Air Force, having finally been proven wrong about Wallis once, make the same category of error again by abandoning the approach that had just demonstrated its unique effectiveness? Drop your thoughts in the comments. If this changed how you see the relationship between institutional skepticism and engineering innovation in military history, hit that like button and subscribe for more history that goes past the surface narrative into the mechanics underneath. Thanks for watching.